So now that we've learned what a function is, we're going to talk about how we can represent them in the real world, how we can give them names, and then how we can evaluate and interpret them. So before we can do all that, there is a form called function notation. So there is a way that we can quickly evaluate functions. And if you look at this equation, we have y equals 2x minus 8. This is a function. This tells us the relationship between x and y in that I can take x, times it by 2, subtract 8, and I get y. That's the relationship it has. But there's another way I can write this. I can write it as f of x equals 2x minus 8. This is function notation. So what I would do is I would circle that box and write function, draw an arrow and say function notation. The f of x is really just a fancy way of saying y. Your f of x is the same thing as your y value. So the way we read it is f of x equals, okay? So it's super important to know that. And what that means is function of x. So when we have x, it gives us our y. Let's go look at that. So we can evaluate a function, meaning we can find what our function's value is. We can find what our output's going to be when we substitute the value in for x. So we put our input in. So when we look at this, let's look at number 1. This is read f of x equals x plus 7. That x in the parentheses is my x value, okay? So when I replace it in this problem, you see how I put 5 in its place. So to evaluate and find the output, I'm going to substitute in 5 wherever there's an x. Then I'm going to go and do the math. And what that means is when it says f of 5 equals 12, it basically means when my x value is 5, my y is 12. So the ordered pair here would be 5, 12. Do we understand? So I want you to try B and C on your own. Okay, let's come look at this one. So same thing. I'm going to replace x with 1. So it says g of 1. Now, I have g instead of f. Sometimes we're going to be faced with a problem that has more than one function, or I'm going to combine multiple functions in the real world. So I can't use the same letter f. So I have to change it and use the letter g. So our most common function notations are f of x, g of x, and h of x. Those are really the ones we see a lot, or h of t or h of something else, and you'll see in a minute. But it doesn't change it. That's still function notation, okay? So in this case, I replace x with 1. I'm going to do the math. 3 times 1 is 3. Then I add 8 and get 11. So what that says is, in this function, when x is 1, my y is 11. So my ordered pair is 1, 11. Does that make sense? Okay, so I want you to try B and C here. Okay, so if we take a look at number 3 and 4, these are a little different. I want you to try these. Replace x with its value in each of them. And we're going to look to see what you're understanding, what you're not understanding. Okay? I want to see if you can evaluate using order of operations. You do not have to do anything else on this page, just up to 3 and 4. Okay, so this is a function. We are at a function. Functions represent real-world relationships. So one of the most common ones that you're going to see in algebra is throwing a ball into the air or throwing a water balloon or jumping off a cliff. We're talking about velocity and time. So look, let's read this word problem. A ball is thrown into the air with an initial velocity of 22 meters per second. The quadratic function, and we're going to spend 2 whole sections on quadratics, but the quadratic function represents the height of the ball above the ground in meters with respect to time. So what this is saying is, once we have our time, we can predict our height. So this is giving us our height given our time. So there's some key facts we need to pull out here. The function itself, height, above the ground, that's super important to understand, and then time. So look at that function. It says h of t. Well, look at our graph, okay? H of t kind of looks like our f of x, right? Where h is our height, t is our time. Then go over and look on the graph. Where's our time? It's on the x-axis. Where's our height? It's on the y. Meaning our height depends upon our time. There's also other stuff we can pull off from our graph. Okay? You can see it's starting at 0 and it's showing the path our ball is thrown. Because when you throw a ball, think of what happens. You throw the ball in the air, it hits its height, and then it comes back down. But also look, our ball didn't start at a height of 0. So what does that tell us? That our ball is maybe on a tee, or our ball is in the air. Whatever that might be, we have to start looking at our axis and what it's meaning. Okay, so let's go do part A. Part A says determine h of 3 and explain what it represents. Well, we just evaluated a function. We took what number was in parentheses and plugged it in everywhere we saw an x. Well, this time we don't have an x, we have a t. So we're going to do the same thing. We're going to replace t with 3 everywhere I see it. So go ahead and do that now. And this is what it should look like. Remember, we've said this before. When you replace a variable, put parentheses, put parentheses around it because it makes a difference for that t squared. That t squared, that squared is only going on the t. So it means I need to square the 3 first. When I do that, I get 9. Okay? Now I can go through and multiply. Negative 4.9 times 9 is 44.1. 22 times 3 is 66. Notice how I'm doing these steps. This is going to help us stay organized. Okay? Then let's go and add. Okay? And I add yet again. So, yes, we found what h of 3 is, but it says explain what it represents. Remember, when we plug this in and get a value, that's telling us our y. Go look at our graph. What is our y? Our y is height. What was our x? Our x was time. Well, in this example, our x was 3, and our y is 27.4. So that tells us that at 3 seconds, the ball is 27.4 meters in the air. Does that make sense? Okay, look, 3 seconds. That's our time. Our time is our x values. Well, if I go straight up, there is my height. And it's about 27.4, okay? So that's showing you how if we can plug something in, we can get its result. So let's go now look at part B. Part B asks, what is a reasonable domain? Remember, the domain of a function is all the possible x values. The graph is representing height in respect to time. So if domain is our x, okay, that's all our time values. So think about this. Think about time. When we talk about time, our ball is going to start at what time? It's going to start at 0 seconds. Eventually, it is going to end. Our time is not going to go on forever. A ball cannot physically stay in the air forever. So if we look at our graph, we want to go up. So it's starting at 0. So our graph went up to 0. But then we come over here. Our graph is about, we can estimate about 4.6, give or take, okay? So when we talk about our domain covers all these x values, and we go from the left to the right. So our domain is between 0 and 4.6. And we have to say equal to, because it's equal to that start and stop time. Okay? The last one is, what's a reasonable range? Well, our range, again, we're looking at height and time. Time was our x, range is our y. So a ball can't go to infinity. A ball has to hit a peak. If we look, okay, our ball also has to hit the ground. So our ball at some point was at 0. But the height of our ball was about 30 meters. So we say that our ball was between 0 and 30. Because at one point the ball was on the ground. And at one point it hit 30 and it was equal to 30. So that's why we have to say equal to. Are we kind of seeing how these functions come into the real world? Okay. So I've already crossed out a couple things for you. The function represents. So let's just pull that out. So let's just start with, here's our function, okay? This is the person's variance, okay? Well, what is variance? What word does it sound like? It sounds like vary, right? Okay, so how much does our body vary? Our body temperature, how much is it different? When X is a person's current body temperature. So that function shows us how much someone's body temperature will vary from its current. Now they also say a healthy individual should be no more than 0.5. So this formula shows us how far someone is from the normal. So if we plug something in, it's going to tell us that person's current body temperature. So let's look at part A. The current body temperature of someone is 99.4. Well, our word problem told us that X is the person's current body temperature. Okay, so remember, it says what conclusion can be drawn. So I'm going to plug in 99.4 into X because that's their current body temperature. And remember, the whole time is that we're doing this, we're trying to come up with a conclusion of what can be said. When I do the math, these two bars mean the absolute value. So the absolute value of 0.8 is just 0.8. So you got to go back to the problem. A normal variance, meaning your temperature can be give or take 0.5 above or below. Okay, so like sometimes your body temperature can be 98.1. If you're super cold, like I've had it before, I actually went and got my flu shot this year and I was at 97.8 because I had just had ice cream. So your body temperature can vary, but they say if you're within 0.5, you're healthy. But this one's within 0.8. So what does that tell us? Well, since the normal variance is 0.5 and this person was 0.8, it would mean they are sick or they're not feeling well. Even if your body temperature is below normal, there's something that could be going on. Okay? So now there's part B and part C. Now that you've seen some functions in the real world, I want you to try these two. Try these two on your own and see what you get. Remember, be sure that you've answered everything I've given you to answer on your own, that you've answered the question at the end of your notes, and feel free to ask if you are lost on anything. This is where we are now applying it to the real world, and it's okay to not get it yet, but you need to ask. Also, don't forget, put a star at the top of your notes and you'll get extra credit.